It is important when you consider experimental work to make sure that you are in a regime when you want to report reaction kinetics that it is free from any artifacts in your reactor, like stirrer speed that can affect external mass transfer. So if I have two runs in the same batch reactor with different agitation speeds of my stirrer, initial starting conditions exactly the same, if I get two rate profiles, lower rate profile with stirrer speed 1 and a higher rate profile with stirrer speed 2, it implies that my reaction rate is not free from mass transfer effects and that the surface concentration is less than the bulk phase concentration. I can say nothing about this run, whether it's free from mass transfer or not. If I do an extra run where my RPMs is, for instance, 1500 and I measure exactly the same concentration profile, then I can say at stirrer speeds higher than 1000 RPMs, I've excluded any external mass transfer effects. I'm in the reaction controlled regime and Ca surface is equal to Ca bulk. In a packed bed reactor, this specifically refers to your TAT 4.1. I can have the same mass of catalyst, but my reactor just looks different. In the one, I've got a high linear velocity because I've got a thin tube, long thin tube, and in the other, I've got a low linear velocity because I've got a short fat tube. So in TAT 4.1, you are given the prediction of conversion that you would get if your rate is free of any external mass transfer effect. So it's reaction rate controlled. Ca surface is equal to Ca bulk, and you can use that information to find your intrinsic rate constant. Now, since you are given the actual conversion also in TAT 4.1, note that in TAT 4.1 you specifically told you've got a first order reaction. You can use the actual conversion to calculate your effective rate constant. Since you are now in a position to know the value of your intrinsic rate constant, you can use that information to calculate KCAM from that information. A very important consideration when we consider external diffusion effects is the effect that temperature may have on our observed rate. So in order to highlight this, let's consider the rate of a specific reaction when we keep the concentration constant. So only thing that will vary is the value of our rate constant as a function of an increasing temperature. So first, we are going to consider the two extreme scenarios when the reaction is rate controlled. That means that no external mass transfer effects affect my rate. Surface concentration is equal to the bulk concentration. The rate will then follow the profile that we know because our rate constant is very temperature dependent. In fact, it is the Arrhenius equation that governs the temperature dependence. When we have external mass transfer controlled rates, the other extreme where the surface concentration is equal to 0 and my rate is only controlled by the rate of external mass transfer, a very limited increase in the rate will actually be observed because there's a linear increase of Kc with temperature. Some textbooks say it's to the temperature to the power of 1/6, and in many cases it's so slow, the increase, that we can actually neglect it. So what is the implication? It's easy to see if we consider the math specifically for a first order reaction. If I have an increase in temperature, what happens to my resistances? This resistance to external diffusion, yes, it does decrease because Kc increases, but there's a very mild decrease, a mild linear decrease in this resistance. The resistance to the actual reaction rate, however, decreases significantly. So because this increases exponentially, there's a very significant decrease in this resistance. So the implication is if at temperature 0, you may start with the two resistances are equal. This is 5 and this is 5, the resistance. This one can very quickly become 0.05 and this one will remain pretty much 5. Think about the effect of the regime where you're in, the effect of surface concentration versus bulk concentration. You need that to answer some of the questions in the test.